Hello all, I'm back with another video. So it's again a past paper walkthrough, and this is for Unit 6, okay, Practical Skills in Physics, number 2, okay. And this is from January 2025, so it's quite recent, okay, I mean just last year. So let's dive in with question and start with question 1. A student investigated the pressure of a fixed volume of air using the apparatus shown. And as we can see, there is a flask with air, there is a pressure gauge, there is an immersion heater with a 12 volt supply, water, and so on. So question A. The student used the immersion heater to heat the water in the beaker. Identify one health and safety issue and how it should be dealt with. So I guess the immersion heater, okay. Okay, and the beaker will get hot. So you will need caution, for example, tongs, when handling the heater, right? So you don't get burned. All right, I think this was straightforward. Let's move to question B. The student determined the temperature theta of the fixed volume of air. Describe an accurate method to determine a single value of theta. Okay, first of all, they don't have a thermometer in this arrangement. Okay, so that's something that you need to think about yourself. So, but it's quite straightforward if you think about it, because how else are you going to measure the temperature? So we can write that the student, okay, can use a thermometer placed near the metal flask. Okay, so near the metal flask. Okay, the water must be stirred. Okay, and this gives me the word stirred. I mean, this gives me the opportunity to make a very lame joke that this reminds me of James Bond. I mean, the nickname of the channel is Dr. No, which is who is a villain in the very first James Bond movie. Okay, so James Bond drinks his what is he drinking, martini or something like that. I don't remember what he drinks, but he wants it stirred and not shaken. So anyway, so the water must be stirred before placing the thermometer in. Okay, before placing the thermometer in the beaker. So the temperature, let's write the temperature as theta, is homogeneous. Okay, if you don't stir it, maybe the water will be locally hotter than the water a few centimeters up, for example. Okay, so you need to stir it so the heat distributes evenly. Okay, part C, the student recorded at a pressure of 110 kilopascals. He repeated the measurement several times as the flask was cooled and reheated. He recorded the following measurements, which are temperatures, and we are given 4 values, so you have to determine the mean value, and we do that by summing the 4 temperatures and dividing by the total number of measurements, which is 4, to find 42.25 degrees Celsius, which you can write as 42.3 degrees Celsius. Okay, determine the percentage uncertainty in the mean value of theta. To do that, we need to know the absolute error in the value of theta. And since we are given several measurements, we have to use the half range. Okay, so the half range is the absolute error. And we find that by subtracting the largest measurement, which is 14.5, minus the smallest measurement, which is 41 over 2. And we find 1.25 degrees Celsius, which is about 1.3 degrees Celsius. Therefore, the percentage uncertainty, let's write it as PU, percentage uncertainty in theta, is equal to the absolute uncertainty, which is 1.3, over the mean value, which is 42.3 times 100. And we are asked for the percentage uncertainty in the mean value, okay? That's why we use the mean value, okay? And this is equal to 3.1%. And that's the answer. Part 3, the diameter of the flask was 15 centimeters. Determine the number of air molecules in the flask. You may assume the volume of air is spherical. Okay, so we are given the pressure, remember, from up here. We can calculate the volume using the diameter. And we can use the mean temperature. So we can use the ideal gas law. So PV is NKT. And since we want the total number of molecules, we have to solve for N, which is PV over KT. And we can write this as 110,000 pascals times the volume of a cube, which is 4/3 pi, times R cube. R is 15 centimeters, so 7.5 centimeters is the radius. So we have to convert to meters, so 0.075 cubed. And then K is 1.38 times 10 to the negative 23. And then temperature, remember, you have to convert to Kelvin whenever you use PV equals NKT. So 273 plus the mean value, which is 42.25. Okay. And if we do the calculation, we find 4.47 times 10 to the 22. Whenever we are asked to calculate the number of molecules or atoms or stuff like that in physics, that number is usually close to the Avogadro's number. Okay, Avogadro's number is 6 times 10 to the 23rd. So we found something that is close to that. It's 10 to the 22, one order of magnitude less than that, but this seems okay. So let's move on. Question 2. A student investigated how varying the power P to a 12 volts filament bulb affected the brightness of the filament bulb. Complete the circuit diagram. Complete the circuit diagram for the circuit the student could use in this investigation. Okay, so first of all, we need a power supply. Okay, so that's the power supply. Then we need something like a variable resistor, so we can change the current in the circuit, okay? And since we are varying the current, it's good to have an ammeter next to the variable resistor to measure the change, the new current, and we can close the circuit like that. And we can also use a voltmeter to measure the voltage across the light bulb. And this is a possible circuit, okay? Part B. The student placed the light sensor at distance from the filament bulb. The light sensor measured X, the light received, in lux. Lux is a unit of measurement for brightness, okay? For the filament bulb, okay? She predicted that the relationship between P and X is given by P equals Kx to the fourth, where K is a constant. Devise a method to test this prediction. You should include the use of a suitable graph. Okay, so it's a 6-mark question, so it's kind of like a long writing, so we can write several points. Usually 6 is good, but if you have 7, it's okay. So let's write that, first of all, you should ensure that the light sensor is at a fixed distance, oops, fix the distance from the filament bulb. Okay, that's the first thing we can write. You should also, excuse me, you should also ensure that there is no background light. Okay. Okay, maybe you can use a dark room, for example. Okay. Okay, and you can use a variable resistor to vary the current in the circuit and measure the voltage across the bulb X for various currents I. Okay, you can measure, so once you have I and V, so you can measure X for 5 different values of power, and power is I times V. Okay, this is from unit 2, by the way. But see how at the A-level physics, usually you need to know stuff from different units. Okay, so this is unit 6, but you're being tested on something, on knowledge that is relevant to unit 2, that is related to unit 2, I'm sorry. So you have to have a spherical knowledge of everything. So, okay. And once you have the measurements, so once you measure, here you can write, yeah, we wrote it 5 different measurements. So once you measure pairs P and X, you can plot P versus X to the 4th, and you should get a straight line with the gradient being K, if it's a straight line. And I think this is a complete answer. So let's move on to question 3. A student investigated the damped oscillations of a pendulum using the apparatus shown. Okay, so you see that there is a string, a stand, a pendulum bob, and a paper cone that I guess creates some resistance, so you have damped oscillations. And there is a half-meter rule, and here they show you the amplitude A. So the paper cone acted as a damper. The student displaced the cone and allowed the pendulum to oscillate. He measured the amplitude A every 5 oscillations and recorded the value to the nearest 5 millimeters. Give 2 reasons why it will not be appropriate to record A to the nearest millimeter. So it is hard to judge. So we can write that it is hard to judge when the maximum A occurs. As the pendulum changes direction fast. Okay, so it will be really hard to determine to the nearest 5 millimeters. And you can also write that you have a parallax problem. okay, as it is difficult to judge when the line of sight is perpendicular to the ruler. Okay, so that's a possible answer. Part B, the relationship between A and the number of oscillations n is that exponential relationship over there, A equals A naught e to the minus lambda n, where A naught is the initial amplitude and lambda is a constant. Explain how a graph of ln of A against n can be used to determine the value of lambda. Let's go take the ln of A. So ln of A is going to be ln of A naught minus lambda nu, which is of the form y equals c, which is a constant, plus x. So ln of A versus n will be a straight line with gradient. Don't know why that pops up in the bottom, but anyway, with gradient equal to minus lambda. Okay, so if you plot the ln of A versus n, you can determine lambda. So let's move on to part 2. The student recorded the following results. Plot a graph of ln of A against n on the opposite grid. So here, okay. Use the additional column for your process data. Okay, so the additional column will be used to find ln of A. Okay, and this is a point where I will cut the video and you will see the results because this is YouTube. Okay. Okay, now that we have the results, we will make the plot. So let's take advantage of the new feature that allows me to draw straight lines. Okay, that's nice. So we have a ln of A here and n down here. So I will use, okay, we'll start from 0 for n, and I will use the squares as 5. So each square is 5. 5, 10, 15, 20, 25, and 30. Since we have plenty of space and we go up to 30. And then for the vertical scale, I guess we will use, let me think. I'm doing this on the fly. So the lowest value is 1.25. So let's start, so let's assume that this is, down here is 1.2. And then this large square is 1.3, 1.4. All right, now that we have the axis, we will draw the points. The first pair is for 5 oscillations, we have 2.14, which will be this point over here. So this one, okay. All right, these are all the data points. Let's draw a straight line for the fit, a best fit line, as they call it. So something like this. So okay, it's not the best line in the world, but we will roll with it, okay? So this is the plot. So let's move on. Determine the value of A naught from the graph. Wait, I think there is one more question. Yes, sorry. Part 2 was drawing the graph. Part 3 is this one over here. We skipped it. So determine the value of lambda from the graph. So the gradient is equal to minus lambda, and it should be equal to, we can take the two extreme values. This is a trick I learned from one of my students, actually. So the extreme values are these. Okay, so let's do 2.14 minus 1.25. At 2.14, n is 5, and at 1.25, n is 30, so we have to subtract that. So we find minus 0.036. So lambda is 0.036. And don't get confused that I took the values from the table. We are using exactly the same values here in the graph, okay? So this point and this point. But if you use the graph, which is equivalent, you can take any 2 points. So you can take this point, for example, and this point, okay? And in this case, you have to calculate what this is, the asterisk, and divide by the other asterisk, okay? So let's do part 4. Determine the value of A naught from the graph. So this is gonna be the, oops, I need the black color. So this is gonna be the y-interception. So ln of A naught is equal to, as you can see from the graph I plotted here, it's 2.24. Is it? Yes, 2.24, which means that A naught is e to the 2.24. And I need to do this now, actually. So I pulled out my calculator and I found 9.39 centimeters. Okay, now part 5. Explain why the value of A naught determined from the graph may not be the true value of A naught. So one reason could be that there might be, okay, a systematic error okay, in the measurement of A. Okay, which might cause the line of best fit to be shifted. In which case we will measure something different for A naught, okay? But this is good enough. So let's move to question 4, which is the last one. Usually unit 6 is always 4 questions, okay? So students set up a ramp as shown. The student placed 2 markers at distance s apart on the ramp, okay? The student used a meter rule to measure the heights h1 and h2. She calculated the difference in height, delta h, as 21 millimeters plus or minus 1 millimeter. Explain why it was appropriate to record the uncertainty in delta h as 1 millimeter. So the smallest deviation of the rule is 1 millimeters, which means that the absolute uncertainty in H1 or H2 is 0.5 millimeters, because it has to be half the smallest deviation of the instrument, okay? Therefore, since delta H is, as we see, H1 minus H2, comma, then the uncertainty, the absolute uncertainty in delta H will be equal to the absolute uncertainty in H1 plus the absolute uncertainty in H2, which is 1 millimeter, okay? And that's the answer. Part B, the student placed a small glass sphere at marker 1, so here, okay? She released the sphere and used a stopwatch to measure the time t taken for the sphere to reach marker 2, so this distance s. She repeated this several times. The student moved marker 2 to the lower end of the ramp and repeated the procedure. So she moved the marker, say, here, and she rolled the sphere again. So the new distance s will be larger. So let's call it s prime, for example. Okay. Discuss how moving marker 2 to the lower end of the ramp could affect the percentage uncertainty in T. So, the percentage uncertainty in T is equal to delta T, which is the uncertainty in the measurement of time, over the total time times 100%. So in both cases, delta T is the same, right? But T total is larger for the second case. Thus, the percentage uncertainty in T is smaller in the second case, because T total is larger. And that's the answer. C. The time T is related to the acceleration due to gravity G by the formula given there. Determine the student's value of G, and they give us S, delta H, and T, as well as the uncertainties. So we can just solve for G now. So G is equal to 14 S squared over 5 T squared times delta H. Okay, so this is equal to 14 times 0.9 squared over 5 times 3.36, and this should be squared, times 0.021, because I converted to meters. The units are meters squared over seconds squared times meters. So we recover meters per second squared, and we find 9.57 meters per second squared. Okay. Part 2, show that the percentage uncertainty in the student's value of G is about 7%. Okay, when we have to calculate the percentage uncertainty of a ratio, we add the percentage uncertainties of the individual quantities. So first of all, let's find the percentage uncertainty in S squared, which is going to be 2 times the percentage uncertainty in S. And I have a video about uncertainties, by the way. Maybe I will link it in the description. So this is equal to 2 times the percentage uncertainty in S. So the percentage uncertainty in S is going to be 0.1, because it's given, over 90 times 100, which is equal to 0.22%. Okay, the percentage uncertainty in T squared is similarly equal to 2 times the percentage uncertainty in T, which is 2 times, as you can see, 0.03 over 3.36 times 100 gives 1.79%. And then the percentage uncertainty in delta H is equal to 1 over 21 times 100. This is the simplest one. So 4.76%. And I'm going to use a clean page to find the percentage uncertainty in G, which is simply going to be the percentage uncertainty in S squared plus the percentage uncertainty in T squared plus the percentage uncertainty in delta H, which is equal to 0.22% plus 1.79% plus 4.76% yields, let me see, I have the results here in my notes, 6.77%, which is indeed close to 7%. So we are good. And finally, deduce whether the student's value of G is accurate. Okay, we can calculate the absolute uncertainty in G. simply by multiplying the percentage uncertainty in G, which we just found, times G. So 6.77 over 100 times 9.57 yields 0.65 meters per second squared. So G is going to be 9.57 plus or minus 0.65 meters per second squared. So the calculation is actually accurate because 9.81 meters per second squared, which is the actual value, is within this range, okay? So the measurement, so let me move over here. So the measurement is accurate as 9.1 meters per second squared is within the range of 9.57 plus or minus 0.65 meters per second squared, and that's the answer. All right, I went over this a little bit fast, but I hope that you guys understand what I'm doing. Please ask questions in the comments. I'm very happy that the channel started growing actually. So thank you guys for following. I hope that you find these videos useful. Please help me grow the channel even more. I mean, the goal would be eventually to, I mean, ideally, if this goes up to, I don't know, 100,000 subscribers, I'm sorry, I might not have to work anymore and I can work on this full time, which is kind of fun. So please, I don't know, share these videos with your friends, family, I don't know, whoever finds them useful. And today I'm recording from my sister's office, by the way. She's a lawyer. Maybe I will add a link in the description. So I don't know, we'll see. Thank you guys and see you in the next video. Bye.